computer. Okay, so now we continue with graph sister algebras. How do I remove it? Oh. Okay, start sharing again. Share it. And so first, let me establish some notation, because you see, first we define path algebras, then we have these strange Greek letters chi, then we divide by relations. So we have chi's in equivalence classes of chi, so we have square brackets. Then we have a tilde construction, which doesn't do anything in this case, and we have a sister completion. If you want to apply all these maps, the notation will be baroque. So I'm trying to simplify it, and let me just say that when I have my graph sister algebra, you remember it's defined as the universal sister algebra of a Leibniz path algebra. Then I have generators labeled by edges and by vertices. So I'm just introducing a notation here. So whenever I have a generator corresponding to a vertex V in E0, I denote it by PV. That's a projection, remember, from the definition of the sister algebra. And a partial isometry corresponding to an edge E will be denoted by SE. This is traditional notation in graph sister algebras. Now remember that according to the definition of the star structure, S of E star, where E star is now a ghost edge, is by definition of star structure the adjoint of SE. Okay. So furthermore, whenever you have a path, you can think, so what is a partial isometry related to a path? Well, this is just multiplication by partial isometry. So S of a path from E1 to En is just a shorthand for writing SE1 times SE2 times SE3, blah, 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 up to Sn. This is just notation, okay? And with this notation, if you rethink our construction, if you bear in mind that the path algebra itself is also a universal algebra given by generators and relations, okay? Then the only additional relations that you have to throw in are the relations which are written here in point number 1, because it doesn't follow from anything else. So if you would have any graph and you would define the universal algebra generated by idempotence, so vertex squared is orthogonal idempotence. Yeah, this is important. Oh, generated by, yes, so it should be added here by orthogonal projections. That should be added here. Sorry. By orthogonal projections. I forgot this word, right? Well, but if V is different from W, then PV times PW is 0. Right? The usual thing, yeah. So you assume what happens when you multiply vertices, and now all this concatenation recipe follows from just condition number 1. Okay, if you assume that concatenation of the vertex, which is the starting vertex of an edge with an edge, is this edge, and you assume the same about the end of this edge, then basically you immediately know that you can concatenate two paths to a longer path, to a non-zero path, whenever the end projection of one path agrees with the starting projection of the other path, because these are orthogonal projections by assumption. Okay. So you can view path algebra as the universal algebra given by generators, which are vertices and edges. Okay, subject just to this relation number 1. That's it. The rest follows. The definition of the path algebra follows. Okay, and then I divide by further relations.
So, sorry, I don't remember this from last time, but like we are multiplying operators following the ordering of the path.
Yes, exactly. Yes.
So the projection is like before the
exactly
because
yeah.
the source is before.
Yeah, exactly. So in other words, I say I have a vertex. I multiply it by an edge starting in this vertex, and this is this edge. I have an edge, and I multiply it by its end projection, and this is this edge. So then it's clear that whenever I have any path here and there, in order for them to multiply to non-zero, these projections have to agree, because I can always stick them out, and because I assume that these are orthogonal projections, if they don't agree, they multiply to 0. Okay, So this is a way of rewriting path algebra as the universal algebra given by generators and relations. And then I just throw in further relations. It's another exercise in abstract mathematics, but if you have these intermediate quotients, then you might as well do just one big quotient. You can have an algebra divided by the other relations. And in this quotient algebra, you throw in more relations in the quotient. But you might as well throw all the relations at once. That's the same thing, just an exercise in pure algebra. Okay. So I can now reformulate my graph sister algebra to be the universal sister algebra for these generators and relations. Okay. That's not a big deal. That's not a big theorem. Although, you know, to be really clean, you have to make some effort to verify things. All right. Good. So now we have a subprojection lemma. I take any graph E and I take its graph sister algebra. Then I claim that for any edge, it is true that SE times S of E star is less than equal to the projection PSE. Okay. And I'm going to prove it using general theory of sister algebras. Now, once I have it, the proof is not so complicated. So for starters, observe that SE times SE star is indeed a projection. Well, so SE star squared. So first you observe that by the definition of the star structure, SE star is SE star. Then you square it. So you write SE star, SE star, but SE star SE is equal to the end projection. Okay, so put PTE here. And remember that the end projection times the edge partial isometry is just this partial isometry, so it vanishes. So I remain with SE as E star, which is of course the same as SE as E star star. So that's self-adjoint, obviously, and it's an eigenpot. Okay. So these guys are projections, and they are sub-projections of the source projection. Okay. I mean, I want to prove. Okay, so now I proved just that this is a projection. Okay, but now we can infer from the general theory of sister algebras, that's what I proved to you, that this projection SE as E star is less than equal to PSE if and only if we have this multiplication recipe. I mean, you have to have that what is supposed to be a sub-projection must somehow absorb the bigger projection. So SE as E star projection times this source projection must be equal to SE as E star. Okay, that's by this general theorem, I believe. So, but the above equality is equivalent to the same equality start. Okay, and why did I? There is some typo. I just want to involution is a bijection. So this equality holds if and only if it holds after I star it. Okay. And if I star it, so just let me write it anew. If I star it, I will simply get a PSE self-adjoint. So I have PSE. Then I have SE star star. So this is SE. Okay. And then I have SE star. And that's self-adjoint. So this is SE. SE star. Okay. But of course this holds because I know that in my sister algebra this path relation holds, right? PSE SE is equal to SE. Okay, so this holds. And I'm done. Okay. But it was so easy because I already have these equivalents. Yeah.
Couldn't we also prove this by saying that we have a sum of finite number of positive operator, which is my projection.
But why is the sum of a finite number of positive operators?
Because like we have on the we define P as like all the projection, all the SE star going out from a given.
Yeah, but what is an infinite emitter? What is the thing?
It was not regular.
No. Did I say regular anywhere here? Do you see the word regular?
But are we like, okay.
I'm not using this relation for regular vertices.
Okay.
There's nothing. In fact, the whole idea is that this is fine-tuned for infinite emitters, where you have no finite sum. Yeah, that's the beauty of it. For things, it's vacuous, but for infinite emitters, this is non-vacuous. Okay. When you have regular, when you have a row finite graph, which means no infinite emitters, something stronger holds. But this I will do later on. Okay. Hold your horses. For the time being, you are really to handle infinite emitters, and I just did it. Okay. Sure. Okay, so now I can claim the comparison theorem, because you see, I defined the graph sister algebra as the universal enveloping sister algebra of a Levitt graph algebra, but that's not the way Kunz, Krieger, Szymański, Rayburn defined it. Okay, this is not the standard functional analytic definition. I think our definition is better, is more natural, but you cannot ignore 40 years of literature. You have to make sure that you are talking about the same sister algebra. So this comparison theorem is very important. So again, I take E to be n a graph, and please note the different font. By this calligraphic C, star of E, I denote the universal sister algebra generated by projections. Again, note the different font, labeled by, and I again should write orthogonal projections. Orthogonal projections labeled by vertices and partial isometries subject to relations. Of course, one of the things you should prove, but that's standard, is that this sister algebra exists. Okay, it's not obvious that it exists, but if you can prove that the other sister algebra exists, it's also not a big deal to prove that this sister algebra exists. But you have to do it separately. Okay, I already use the fact that I had the universal sister algebra for subgenerators and relations. Okay, which should be proven separately because these are slightly different relations. Okay. But the basic thing, I mean, once you have a Hilbert space representation for the other relations, you can easily have it for these relations, and you still have the main basic property that your generators have norm 1 at most. Because you're talking projections of partial isometries. The norm is bounded by 1 in any representation. So the supremum exists. Okay. So that's not a big deal, but you really should check that such a universal sister algebra exists. Okay. And now you see that my relation number 1 is the usual Kunz-Krieger, and my relation number 2 is the usual Kunz-Krieger, but, and this is the way these people in functional analysis define graph sister algebra. For an infinite emitter, they say that SE star must be, it's an assumption, a sub-projection of the source projection. That's exactly for infinite emitters. Okay. And now I claim that the canonical assignment of generators, just changing fonts, defines a star isomorphism from the usual, from the graph sister algebra as we define it, to this calligraphic graph sister algebra as is usually defined by people in functional analysis. Okay, so I claim that this is an isomorphism, and here's the proof. So we already know by the subprojection lemma that phi is a well-defined star homomorphism. The star homomorphism by construction, because you do it on generators of a star algebra. And on the side of wait a second, did I do it? Where do you have fewer? Maybe I reversed the arrow. Okay, you have more relations on the side of a graph system. Oh, okay, sorry, this phi should be in the opposite direction. Okay, why? Because after we proved this subprojection property in the graph sister algebra, we just proved it. Okay, I know that all relations satisfied for the calligraphic sister algebra are satisfied over there. So this is a well-defined star homomorphism. Okay, because all relations are satisfied. And now, in order to prove that this is actually a bijection, I must prove that the inverse canonical assignment on generators is also a well-defined star homomorphism. So the only thing I have to prove that these missing relations are satisfied. And the only missing relations in this calligraphic sister algebra are these coming from path algebra, because everything else is satisfied. Okay. Number 3 is satisfied, number 2 is satisfied, number 1 is satisfied. Okay. Because if you remember how we did this presentation of a graph sister algebra, that's this part here. Okay. We have condition number 3, it's by assumption. We have condition number 2, it's by assumption. But we have condition number 1, which is not assumed in this calligraphic sister algebra. Okay. So you must prove that it holds in the calligraphic sister algebra to make sure that the inverse assignment is well defined. I mean, the inverse assignment defines a star homomorphism. Okay. So that's the only thing we have to prove. Oops. That's too far. And when we do it, we are done. The theorem is proven. Okay. I'm not writing it explicitly because it's really boring. I just change fonts. I write that for every edge, calligraphic SE is mapped to non-calligraphic SE. For every vertex V, calligraphic PV is mapped into non-calligraphic PV. Okay, so I have an obvious bijective assignment on generators, and now because I'm talking universal sister algebras, all that I need to do is that this assignment satisfies the ideal of relations. Okay, but if this is satisfied, then by the universality of the sister algebra construction, you really have a star homomorphism of the whole sister algebra.
We reserved the room actually. Was it reserved here?
Yes, from 2 to 4 o'clock. Yes.
So we made a reservation from 3 to 4. But we moved.
Okay, so yeah, I mean, surely have it reserved. Okay, so right, so you see, that's why I go from this calligraphic sister of E to graph sister algebra, because I repeat, I have fewer relations on the calligraphic side. Okay, I don't have this relation. On the non-calligraphic side, I proved this infinite emitter relation. I proved it for all edges, so in particular for infinite emitters. Okay. But for finite emitters, this is actually trivial. This inequality is trivial for finite emitters. It's non-trivial for infinite emitters. Here's a proper assumption. Okay, it doesn't follow. So I have a well-defined star homomorphism from the calligraphic side to non-calligraphic side, and to prove that it also exists in the opposite direction, which makes phi a bijection, I have to prove that the relations in this calligraphic universal sister algebra imply the relation which I assume on the non-calligraphic side. And that's this relation for, multiplying the vertices with edges starting at these vertices, or multiplying edges with vertices at which these edges end. Okay, that's the only thing I have to prove. And to this end, I prove the so-called concatenation lemma, because that's what allows me to see my multiplication in a graph sister algebra by concatenation, as in path algebras. This is what actually relates my graph sister algebras to path algebras. And because it's not such an obvious argument, this is why people overlooked it for 24 years. I mean, it took 24 years for people to realize that graph sister algebras actually come from path algebras. It was only in 2004 that Abrams and others, Ferrara, realized, wait a second, I mean, what these people like Kunz and Krieger, Szymański, Rayburn are talking, they're just talking path algebras divided by stuff. You know? And Kunz algebra, famous Kunz algebra, is nothing but the completion of a Levi algebra. This was realized like 24 years later. And the reason is here, because it's not so obvious. I mean, when you are set to think about it, you prove it. But you don't notice it randomly, okay? All right, so let's prove this concatenation lemma. Basically, we have to do two calculations. One calculation is, both calculations are easy, but the first one immediately gives you the result. So I want to prove that SE PTE is equal to SE. So I subtract SE from PSE SE. and I star it and I multiply it by itself. If I prove it 0, then by C-star property, I have the desired equality. Okay, so I just calculate. When I star SE, PTE, SE, I have PTE because self-adjoint times SE star. So first I multiply SE PTE, so I have PTE, SE star, SE PTE. Then I multiply SE, so I have PT, SE star, SE with a minus sign. Another minus sign is here, minus SE star, SE PTE here, and I have plus SE star, SE. But now this is easy because remember, SE star, SE is just PTE by the first conspicuous relation. So I have PTE cubed minus 2 PTE squared plus PTE. And of course, this is 0, right? Because I have twice the projection minus twice the projection. And I repeat by the C-star property, I know that this element in my C-star algebra is 0. Okay? Because basically what I'm telling you is that the norm squared is 0, so the norm is 0, so the element is 0. The other way around is tricky. And this is when I need this big theorem from C-star algebras about subprojections. Okay? So now because I'm talking about initial projections, I have to take the star on the right-hand side, but the effect is the same, okay? Because if I prove that XX star is equal to 0, then X is equal to 0 just in the same way. I mean, if you want a legal argument, then write X as X star star. And okay, so say that we prove that X star is 0, but star is a bijection, so also X is, okay? So we do this calculation, but now we start the right-hand side. So the right-hand side becomes SE star, PSE, SE star. So I have PSE, SE times SE star, PSE. Okay. Next, I have PSE, SE times SE star with a minus. Then I have minus SE times SE star, PSE, and finally I have plus SE, SE star. Okay. But now I can argue as follows. Remember that we are in this calligraphic C-star algebra. So we know that SE star is a subprojection of PSE. So now by this difficult part of the equivalence, okay, I know that the inequality implies equality in multiplication. I know that this guy multiplies to PSE. Okay, because I assume that SE star is less than equal to PSE. Now you can say, wait a second, but you claim it only for infinite emitter. Okay. So let me explain. Obviously, SE is not the sink because it emits E. All right. So if it's an infinite emitter, I'm done by assumption. If it's a finite emitter, then I have this finite sum. But then I have a finite sum in which I have SE star plus something positive is equal to PSE. Okay, this is for a regular vertex. Okay, then obviously I can say that PSE minus SE star is positive. So it means that SE star is less than equal to PSE. Okay, so when you have a regular vertex, that's not by assumption, it's by the second Woods trigger. Okay. Okay, so this is why didn't you correct me? Of course, it's not PSE, it's SE star. Why didn't you yell at me? Ludwig, I'm not paying attention.
Yes.
SE star is a sub-projection of P, so it absorbs P. Okay. And the same is here. Why? Well, you can say, well, but it's on the wrong side. Well, forget it. I can take the adjoint and P is self-adjoint. It works. Okay. And the same here. It's on both sides, but again, whichever side it is on, you can absorb it. So you end up with SE star minus 2 SE star plus 1 SE star, which on a good day is 0. Okay. So we also have at SE, and again, another typo. SE PSE is equal to SE. Okay, So this relation is satisfied and the inverse star homomorphism exists. So the comparison theorem is really true. Okay. So the old-fashioned definition of a graph C-star algebra using the spectral property for infinite emitters is actually equivalent to our definition of graph C-star algebra as the universal enveloping C-star algebra of a Leavitt path algebra obtained from a path algebra. Okay. Sure.
S minus S is
The order PSE times SE.
Oh, yes, this is copy and paste. Thank you so much. Yes, of course. I made two mistakes here. It's PSE, SE, minus SE. Of course, this is what I'm computing. Sorry. You know, I just copied and pasted from the previous line, and I didn't correct this. This is a typical copy and paste error. Okay. Yeah, thank you so much. That's important. Okay. And now we will do row finite as you want. Now we will use this regular vertex property. Okay. So I have the following theorem. Now, to make your life even more difficult, I'm going to give you a third definition of a graph C-star algebra. But it's called only for so-called row finite graphs, which means graphs without infinite emitters. There are many interesting examples of such graph C-star algebras, but also, you know, it's very, very frequent that very, very natural examples are not row finite. So you cannot limit yourself just to row finite graphs. Yeah, that would kill half of non-primitive topology. Okay, but if you're row finite, then your definition of a graph C-star algebra is even simpler. Again, I forgot to write orthogonal projections. Okay, so let E be a graph without infinite emitters. This is so-called row finite graph. And C star E, mind you, now I have this straight font. So it used to be italics, calligraphic, or straight. Okay. So I have a C star of B, B the universal C star algebra generated by projections against straight P, and partial isometries against straight E, subject to relations. And you can see that the relations are very much as before, except you have no infinite emitter, so 3 is gone. But most importantly, I do not assume that SF star SE is equal to 0 and F is different from E. I do not assume it. I'm going to prove it. But it does not follow for all graphs. It follows only for row finite graphs. Okay. So the previous was full equivalence. You can have uncountably many edges, whatever. Nothing was assumed. These are the same C-star algebras, just differently defined. Old-fashioned way, modern way. But here, and you see it in some papers, and it might be confusing. People say, okay, we study row finite graphs in this paper, and by definition, graph C-star algebra is this one. So wait a second, what happened to orthogonality of ranges? Well, nothing happened, it follows. But we prove it. Okay. Again, I have a canonical assignment which just changes the fonts. And obviously you have fewer relations on this straight C-star algebra side. So the star homomorphism exists from the straight C-star of E to the calligraphic C-star of E. Okay, because you have fewer relations on the left-hand side. So all the relations which are in the straight C-star algebra are satisfied in by assumption of the calligraphic C-star algebra. So in order to prove that we have the assignment the other way around, we just have to show that in this calligraphic C-star algebra, that in the straight C-star algebra, this additional property that you have assumed in the calligraphic C-star algebra is actually satisfied automatically. Again, if you want to be really strict, you have to prove first that the straight C-star algebra exists. But it's trivial. It's not a big deal. Okay. So here's a proof, and it's actually nice, I believe. So as we discussed, phi is clearly a well-defined star homomorphism. And to show that it's bijective, we need to prove this property, that if I have two different edges, E and F, then SE star times SF is 0. That's it. That's what we have to prove. Okay. And now, arguing as in the proof of a concatenation lemma, we first see that if you write a SF, then you can multiply it from the left by PSF without changing it. So PSF SF is SF, and PSE SE is SE. I wrote it on the right because you remember PSE is self-adjoint by assumption. So this is so S star PSE is the same as PSE SE parenthesis star. Okay, but I still have to prove here that I have this path algebraic property. But let's go back to the proof I did in the calligraphic case and see that I'm not using any properties that are not given to me in the straight case. I mean, it's proven by this calculation, okay? And I'm just using the C-star property, nothing else. I'm using the C-star property and I'm using this absorption property, okay? But this absorption property, whenever you are rho finite, I already argued for it. When you are rho finite and you don't have an infinite emitter, you have an SE star as a subprojection of PSE always because of the second Kunstberger relation, which is assumed, okay? So that's what we already discussed. So I do have an SE star as a subprojection of PSE. I have a general theory of C-star algebras telling me when I can replace it then by equality, and that's what I'm doing here. So this is why it's completely legit on my side to say that, aha, so now arguing as in the proof of a concatenation lemma, we see that SE star SF is SE star PSE, PSF, SF. So we are done whenever E and F begin at different vertices. Then we are done because PSESF is 0 and the whole thing is 0. Okay. But what if they start at the same vertex? Here fun begins. Okay. So otherwise, remember that there are no infinite emitters. We note that by the second Kunstberger relation, F and E begin at the same vertex, say SE. Then I can write SE star plus SF star plus something positive, perhaps 0, is equal to PSE. All right. But now remember this property that conjugating positive is positive. So I'm conjugating it by SE. So SE star on the left, SE on the right. I do the conjugation. So with the first term, I obtain SE star SE times SE star SE. Then I have SE star SF times SF star times SE. And when I have SE star times something positive times SE, and on the right-hand side, I have SE star PSE, SE. Okay, so here, first you observe that this guy is nothing but P TE squared, which is PTE. Okay. Okay. Now, that's something again positive, remember, general property. So that's positive prime, perhaps. Okay. So this is my new positive. And now look, I still have this absorption property. So PSE SE is actually SE, SE star SE is actually PTE. And guess what? So I claim that these two terms simply cancel. And now I'm just rewriting what is SF star SE. This is SE star SF. Okay. So this is just rewriting this term. Plus something positive is equal to 0. And now remember the lemma, if the sum of the positive elements is 0, then each of the summand is 0. All right, so now I can claim that this left summand is 0. Well, but this just means that SF star SE is 0, and that's what we're supposed to prove. Okay. So this ends like the general theory of graph C-star algebras. I picked up things which you cannot find in books. Of course, I mean, there are many books, there's lots of literature about graph C-star algebras, Levitt graph algebras, but this general theory that I showed you, you will not find it in a book. That's why I decided to do it in detail, okay? Including some arguments from general theory of C-star algebras so that you know what you're standing. And the rest of the lecture, we can just have fun looking at examples. So that would be a good time to ask any questions. So we are done with hard stuff, with proofs and, seeing what's going on. Now we are just going to see pictures. So any questions thus far? Okay. So let's do it. So these are so-called Waxman-Sobelman spheres. And you take, say, n vertices. And if you take n vertices, that you will have a graph sister algebra, which is isomorphic to the so-called Waxman-Soibelman quantum sphere. These animals occurred in real life like this. People invented quantum special unitary groups. This is a fundamental work of Voronovich, published in Invenciones. And then among the general theory, you have some specially preferred Q deformations, like one parameter deformations of special unitary groups. And then you just recall from high school that you can realize odd spheres as dividing SUN plus 1 by SUN and stuff like this, you know. So in terms of sister algebra, it means that you take some fixed point sister subalgebras, and inside sister algebras of SUQNs, you have sister algebras of the spheres. And this is what these guys, Waxman and Soibelman, did. And basically what you do, like in the usual sphere, you have to have 2n-1 sphere. What you do, you have n complex variables that satisfy sphere equation. Okay. So when you look at how Waxman-Soibelman spheres are constructed, well, it's very much the same thing. You have n generators, and you have some relations, but these relations are difficult. All except one of these generators are not normal. They do not commute with their adjuncts. So in fact, we have like two sphere equations, because you no longer can write, you know, if you write z I star zi, well, in general, it's different from zi star. So what should you use for a sphere equation? Well, we have two equations that differ by some powers of q. Okay. So basically, you have a nice sister algebra coming from quantum groups, which is a Q deformation of the usual 2n-1 dimensional sphere. And you have some very non-trivial commutation relations, and you have a sphere equation. And this is the Waxman-Soibelman quantum sphere sister algebra. So to realize that the graph sister algebra is such a graph is very non-trivial. The isomorphism is by all means non-algebraic. So the way, I probably mentioned it, but let me reiterate, the way you prove that your sister algebra is isomorphic graph sister algebra is that you represent both on a Hilbert space in a faithful way. And when you find some nice unitary operator in a Hilbert space that conjugates these two representations to each other, then you know that the sister algebra is isomorphic. But there is this roundabout way for B of H. Okay. You cannot just write algebraic formulas typically. These are totally different animals, these generators. If you want to have some kind of an intuition, then you should think that, you see, for instance, in Waxman-Soibelman spheres, there's some parameter Q. You have some Q, which is non-negative and less than 1. For Q equal 1, you get commutative sister algebra and so on and so forth. But there's no Q in graph sister algebras. Well, the reason is that all these sister algebras are isomorphic, whichever Q you choose. And somehow when you choose P equal to 0 and carefully look at the presentation, then this is basically something like a graph sister algebra, but not quite. Let me elaborate later on the example of quantum distance. That's the picture you should have in mind. And in particular, if you like quantum groups, you know, free sphere is SU2, right? So you might assume that the Waxman-Soibelman quantum free sphere is actually the same sister algebra of the famous Voronovich quantum SU2. And in fact, it is, right? And then when you have n equal to, I want to have 3 spheres, I have to take n equal to 2. So this means 2 vertices. So this means that my graph is only that part. Okay. I mean, here the rule is very simple. I have n vertices. At each vertex, I have a loop of length 1. And then my vertices are ordered from left to right. And from each vertex, I have one edge to every vertex which is further on. Okay. So I go from V1 to V2. I go from V2 to V3 and blah, blah, blah to V2 to Vn. And from V2 to V3, from V2 to V4, and so on and so forth. This is how this graph is constructed. Okay. So when I have only 2 vertices, that's it. I have 2 loops and 1 edge. And this is the famous SUQ2 sister algebra. I told you these are sister algebras, but you can see. Yeah. I mean, it's amazing that you can have this quantum space And as I will try to show it to you later on, you can actually do some surgery on it. And you can construct spaces by push-outs of graphs. Yeah.
But like the commutative case,
Mhm.
how this can be recovered from the graph?
No, no, the graphs, you see, the thing is here you have strictly less than one. Okay.
Plus one is the commutative.
Yeah.
The
Would be commutative.
commutative is classical.
Yes. Yeah.
SU2.
Yes.
Yeah. So you see here we have a Q. And if you define, so this sister algebra is intrinsically defined by Q generators and relations. You have a continuous field of sister algebras, okay? And where Q is equal to 1, your sister algebra is commutative, and its spectrum is exactly a 2n minus 1 dimensional sphere, okay? So if you want C of S to n minus 1, 1 is just the sister algebra of continuous functions on 2n minus 1 dimensional sphere. Okay. But when your Q is less than 1, but bigger than equal to 0, this definition of a sister algebra still makes sense. And now for each and every Q, it is isomorphic to the graph sister algebra of this graph. So the drawback of having a graph that you don't see that it approximates anything. It's rigid, it's frozen. It's sort of at Q equals 0. Yeah. But when you present it in this dynamical way by Q generated relations, and then you vary Q when you have your field. And then you go from this Q equals 0 to Q equals 1, and lo and behold, this is the commutative fiber. Okay.
So which means that for all Q between 0 and 1, they are isomorphic. The sister algebra.
Yes.
As isomorphic, yes, that's true. That's true. Why are you surprised?
Yeah, I mean this. Yeah, I don't get this intuition why they're isomorphic.
I will show it to you on a simpler in a simpler case of a quantum disk, okay? Where relations are. What? Oh yeah. This is a different theorem, and it's far more difficult. You can prove that when you vary Q, your quantum groups are non-isomorphic, because if you want to have an isomorphism of quantum groups, you not only have to have an isomorphism of sister algebras, but this isomorphism of sister algebras has to intertwine with the product, and it doesn't. Okay. So for every Q, you get a different quantum group. Okay. So as you, I don't know, 1 over square root of 2 is as a quantum group different from 1 over square root of 3 quantum.
Quantum group is sister algebra
plus some other structure. And these isomorphisms, I told you, are very non-algebraic. So shouldn't be surprised that they do not respect some other structure. Okay. All right, but the sister algebras, they are one and the same thing. Okay. And now you should think about spheres as spaces that bound balls. Okay. And here's an interesting situation because these balls, okay, so here these spheres existed long before Hong-Szymanski proved them to be graph sister algebras. But these quantum balls were actually defined by Hong and Szymanski as graph sister algebras. Okay. You can still have some nice presentation by Q generators and relations, but here the situation was kind of reversed. You first had the graph sister algebra, and then you relate it to the quantum sphere. And you see the difference between this graph and the previous graph is that I have no loop here. So this loop is gone. Okay. This loop is gone. And well, if you want to see a sphere as the boundary of your ball, well, then you have, so this is 2n minus 2 dimensional ball. So classically you have V 2n minus 2. Okay. And okay, let me do Bn, B2n. Okay, you agree that the boundary of a 2n dimensional ball is 2n plus 1 dimensional sphere, right? Sorry, 2n minus 1 dimensional sphere. Okay. So imagine that here you have n plus 1 vertices. Here I have n plus 1 vertices, and here I have n vertices. Okay.
Yeah.
So in fact, you should think that here I draw one more vertex and all these necessary edges.
Football always not a good example. Not much
What?
football. Soccer.
Yeah, I mean, I'm talking odd dimensional spheres.
Yes.
Yes.
You cannot visualize. Like
Yeah.
this.
Yeah. Okay. So imagine the situation. Now I have my when I have n plus 1 many vertices, this is my B to n ball. And when you remove this vertex without the loop and all edges which end there, then what you get the graph of 2n minus 1 sphere, quantum sphere. Okay. And this is as it should be, because the bounding sphere should be a subspace of the ball. And the same happens with graphs. If you look at this S to n minus 1 graph, this is a subgraph of this graph, where the difference is that what you do, you kill this projection and you kill all edges that end in this projection. Yeah, because if here this is my vertex number n plus 1 and I kill it, this loop is not here. Okay, so let me erase this. I kill this n plus first edge, sorry, vertex. Okay, so if I have n plus 1 many, then this is b to n ball, because you see number of vertices minus 2. So if I put n plus 1, I have 2 times n plus 1 minus 2, which is 2n. Okay, so I kill this vertex with number n plus 1, and I kill all edges that end there. But what I get exactly the graph of a sphere. So the graph of 2n minus 1 quantum sphere is a subgraph of the graph of a 2n quantum ball. So like in the classical case, spaces are gone. But now I can conveniently think about these non-commutative sister algebras in terms of graphs. And still the functor is kind of contravariant. So if I have surjections on sister algebras, I have injections at the level of graphs. Okay. So here you can see that the Waxman-Soiberman quantum 2n minus 1 sphere is the boundary of the Hong-Szymański quantum 2n ball. Okay. And you can also easily see that you have a surjection of sister algebras, because I just take the canonical map. I map generators to generators, with the only exception that this projection and all these partial isometries are mapped to 0. You obviously get a C star epimorphism. Okay. There's one very important thing which I should have defined for graph sister algebras, and I forgot. So let me do it right here, right now. Let's go back to the definition of a graph sister algebra. Oh, yeah, this will be convenient. Okay. So I claim that on every graph sister algebra it has so-called gauge action. Right. I should have one more slide about gauge action. So I have an action of U1 on the sister algebra, which means that I have a group homomorphism from U1 to automorphism of my sister algebra. And because it's the universal sister algebra, I can just define the action on generators and verify that the relations are satisfied. Okay. So the definition is as follows. So let it be alpha. Okay. So alpha would index lambda as an automorphism. So alpha lambda on a projection is just this projection. But alpha lambda on any isometry, by definition, is lambda times this isometry. Well, lambda is a unitary complex number. So you can see that if you do it for all these relations, it's satisfied. So you look at property number 1. Okay, if you look at projections, well, projections are invariant, so that's obvious. Now here that I say partial isometries is kind of redundant, because that's actually input into my second relation, that they are partial isometries. I no need to verify anything. Now, when you look at the equation number 1, I just rescale it by lambda on both sides, so the equation is preserved. And I look over there, the right-hand side is invariant. Well, but so is the left-hand side, because I multiply SF by lambda, but SE star I multiply by lambda bar. That's the property of involution. Okay. If I multiply SE by lambda, then SE star is multiplied by lambda bar. So I have lambda bar times lambda, which is absolute value of lambda squared, but this is a unitary number, so it's 1. Okay. And the same story is here. Right hand side is invariant, and the left hand side you can verify that you just get lambda times lambda bar, which is 1. Okay. So this action is well defined by the universality of the system. And this is so-called gauge action.
So can we think of this as a grading?
Yes, of course. Very good point. Thank you. Yes, it is true for all sister algebras that if you have a sister algebra quick with a UN action, it means that you have a grading by integers. Just basically take the Piotr dual. And it's very easy how you define these components. You look for homogeneous elements of a property that alpha lambda acting on X must be equal to lambda n, where n is any integer, not necessarily a natural number, times X. Okay.
So basically, like projections, they are of degree 0.
Yeah, you can do integration and so on. I mean, have nice. You can integrate this action, the circle action over the circle, and you can get this.
I think it's in the definition. The projection is 0, degree 0, right? And then this S is degree 1, and S star is degree 1.
Yeah. But so, what's your point?
Yes. Yeah. That's. And then this way, I think it's easier to check. It's like all these relations preserve this gradient.
Yeah. But I think there is nothing complicated in the way I put it. The relations are satisfied. It's trivial. I mean, it's obvious. Yeah. But the thing is that in full generality, I prefer to give a general argument. I mean, on any sister algebra, forget graph sister algebra. Circle action means grading. So forget projections and isometries. I mean, that's confusing because you are using properties of a sister algebra that are irrelevant for the Z grading. Any UN sister algebra is Z grading. So forget isometries, projections. It's not important. Yeah. And the way you get this grading is by the equation I gave you here. And when you want to define these Banach spaces that you can get out of it, you just do integration. Circle is compact, so you can integrate its action. Yeah, that's in every book. Okay, so yes, you have a Z grading, and if you want to go back to path algebras, you can view it like this. Let me actually go back. That's the advantage of having slides.
So it means it counts on some one action.
No, there's no. You exaggerate.
So what you want to say when you're going back to the
Well, if you listen, you will hear. Oh, this one. You see, I have this decomposition here. Okay, so I have a natural n grading for path algebras. But remember that when I go to Levi path algebras, I go to the extended graph. So I have ghost arrows. So if you just assume that these start edges are of degree -1, then actually when you look at FPE bar, this is graded by integers. Okay, but you have to go to the extended graph. Yeah. And this grading of integer is respected by this ideal. So now your remark is important, but you can see, look, that this ideal is preserved by the circle action, that everything is fine over there. So when you divide a graded algebra by a graded ideal, we have a graded algebra. Yeah. So stuff like this. Okay.
So really somehow linked to the length.
Exactly. Absolutely yes. Yes. Absolutely yes.
Yeah, that's exactly.
Yes. Yep. Yeah. But you also have negative lengths and so on. Yes.
When we usually talk about gauges,
Mhm.
gauges,
Yeah.
we meant something which is local. I mean, our phase may vary from point to point in the number.
Not always, there is kind of second kind of person. That's not those
That global action then. Well, this is not, in my opinion,
It's not second kind of interaction.
but
It's less kind of this.
like a global transformation to use it.
So,
Ah,
first type of person. I mean, the old physical interaction, now it's like this type.
Well, but let me answer it this way. Basically, what you have here is very much like a principal bundle. So if you say that the structure group of a principal bundle is a gauge group, then when's the name? Yeah, the intuition you should have here is the following. How do we define projective spaces? Complex projective space is defined in the following way. You have your 2n minus 1 dimensional sphere. Of course, you have a diagonal circle action. You scale all the generators by the same phase, okay? Then the sphere equation is preserved. So this is a well-defined action of a circle on S2n minus 1. You divide by this action, and by definition, this is CPN. Okay? Viewed as a quotient space of S2n minus 1 by the circle action.
So the very geometries.
Hmm?
Yeah, you know, the very geometry defined.
So you speak at the same time, so I don't understand.
Not the very geometry, this set of lines.
Yes, it's one of many equivalent definitions, but it is one of,
I think it's 2n plus 1.
no,
Oh.
no.
Or not, it's, yes, so 6n minus 1.
Just take n equal.
And equal to 1 is not
Yes.
quotient.
Oh, sorry. Yes, so it's n minus 1,
Yes.
not plus 1. So I was right to say no.
No, my it's correct. My
Yeah, sorry. Of course, for n equal 1, we have a circle divided by the circle is a point, and the point is CPC. Yes, of course. Yes, yes. But I mean, this looks ugly, so I can write plus 1, and and then, yeah, thank you. Yes, of course. Okay. And here U1 is your gauge group if you want. It's a structure group of a principal bundle.
Still is say gauge group is UN as UN since you go you want. But the gauge second kind is from random you want. So then a lot is quite clear.
No, okay, but like this structure is defined above actually. Would that mean and also if the page is actually to the like all the structure or invariant also if the page
No, I think his question would be if you could define different or different nuance or different isometrics. But then
Yeah.
you should have to define also projections.
I mean, this is not the only U1 action you can have on your sister algebra. That's clear. Yeah, but you have to be very careful. So you have to get length spaces, to get quantum length spaces, and our next talk on Wednesday about quantum length spaces is exactly that you have some fancy way of defining U1 action on the sphere. Even in dimension 3, if you do non-diagonal circle action of a free sphere, you have very beautiful non-trivial length spaces that, for instance, serve as textbook examples of showing spaces that are homotopic but not homeomorphic. So that's a bit tricky, Give me an example of two homotopic, say, three-dimensional objects that are not homeomorphic. And length spaces serve as example. Okay. But it still doesn't matter. I mean, you have a free action, you have a principal bundle, and here this gauge action. I repeat, this gauge action is just a name, and if you want to call structure group for a principal bundle a gauge group, then it agrees. If you don't, then it doesn't agree. That's a principal bundle picture. That's a period mathematics. Whether we want to call it gauge or not, I don't care. This is terminology. But when you say gauge theory in physics, like Yang-Mills theory, this is a theory of principal bundles. Okay. Okay, I think enough about terminology. So basically, what you do, you take this Waxman-Soibelman sister algebra, and you have this gauge action, and then you define, and now it's really the definition, the fixed point sister subalgebra is by definition this CPN minus 1Q sister algebra. So that's the definition. Okay. I take my graph sister algebra, I have my gauge action, I compute the fixed point sister subalgebra, and because of geometric analogy, I baptize the space as the sister algebra of a quantum complex projective space in dimension n-1. Sorry, not n-1. Okay. But now there is some general theory for these fixed point subalgebras that these subalgebras are called core subalgebras. You know, the hard core of a graph sister algebra is this fixed point sister subalgebra of gauge invariance. Okay. And one of the incredible properties you get that these are approximately finite sister algebras, so pretty Gaston's. These are all approximately finite sister algebras. Now, among sister algebras, you can have particularly tractable sister algebras which are approximately finite. They can be written down as limits in the right categorical sense of finite dimensional sister algebras, which basically means matrix algebras. And many kind of Bratelli diagrams classifying them. And basically, if you have isomorphism on K theory, you have isomorphism for sister algebras, there's a lot of yoga attached to it. Yeah. So approximately finite sister algebras are infinite sister algebras in general, but that can be nicely approximated by finite dimensional sister algebras. Okay.
Is this in general context or like just for this example?
I mean, what I'm telling you about approximately finite sister algebras is in general context, and in particular, all core sister algebras of graph sister algebras are approximately finite. All.
It's the invariant part.
The invariant part.
The rest is not.
The rest is not. Yeah. But the fixed points are always approximately finite. Okay. It's a matter of life. So, but here something beautiful happens. It's not always true that the fixed point sister subalgebra of a graph sister algebra is a graph sister algebra. It's not always true. Okay. But it is true here. And see what happened to my graph. Loops are gone. We're killed, you know. But somehow you could at least naively think this way. Well, how about paths? I mean, it's true that here I have only single edges, but you know, going from V1 to V2, I need not go straight from V1 to V2. I can go a million times around the loop and then go to V2. So in a way, you have countably infinitely many paths from V1 to V2, from V1 to V3, and so on and so forth. And now these paths are sort of abbreviated to edges. And this is kind of intuition you should have what happened here. But strictly speaking, I take the graph sister algebra for this graph, and this is not row finite, okay? So here, every vertex is either, there are no regular vertices. The set of regular vertices is 0, is empty. Because each vertex is either an infinite emitter or a same. Okay, so no second Kunstfigure relation. It's not here. But we have these subprojection relations. They are here. Okay. All right. And here in particular, you have a famous Podlej sphere. So if you have n equal to 1, then to 2, then 2 minus 1 is 1. And what is quantum CP1 is a 2 sphere, right? So then that's your graph. And this is the sister algebra of a standard Podlej quantum sphere, which is the minimal unitization of compact operators. Okay, so let me write it like this, that if I take compact operators and minimal unitization, then this is the graph sister algebra for this graph. Okay, that's why I asked this question about minimal unitization, because in non-Kuhn topology, for us, it's obvious. I mean, these things we eat for breakfast every day. Okay? And then the moment you realize, wait a second, this is a graph sister algebra for compact operators. Well, you also have a graph, C star of this path marching off to infinity. This is compact operators. So this is why we bother about these minimum monetizations, okay? So that's why it was clear to us when we can do it like this. Okay. Now, before we move into some surgery, I promised you, yeah, but okay, it's actually, this graph is over here. So this is the quantum disk C-star algebra. So this is the ball in dimension 2. Remember, I have just 2 vertices, okay? So this is a 2-dimensional ball, which is a disk. That's a quantum disk, if you want. And you can do the following. You can write the C-star algebra generated by one generated the following relation. X star x minus q xx star is equal to 1 minus q. All right.
Q is from 0.
And q is from 0 to 1, and both of them included. When you don't include the 1, you immediately realize, okay, that that the norm of x is 1. You can just prove it in any representation, in a bounded representation. So you can throw in this norm condition without any price, without changing your C-star algebra. Okay. And when q is equal to 0, you just get a commutative C-star algebra, because for q, sorry, when q is 1, you get that x is a normal operator with norm 1. So what is the C-star algebra, commutative C-star algebra generated by the normal operator of norm 1? These are all functions on the disk. Okay. But when q is strictly less than 1, you get something funny. And when q is equal to 0, well, then you just get an isometry, the isometry, you get the universal C-star algebra generated by the isometry. That's the Teplitz algebra. This is the quantum disk C-star algebra. And you can prove that for any q, the C-star algebras are isomorphic in the following way. If you want to go from, so okay, maybe for q equals 0, I'll be denoted by s to avoid confusion. All right. So to get from x to s, you have to normalize it. You somehow multiply x by something positive, which is invertible. And this is your s. But that's a C-star algebraic operation. I'm taking an inverse of a positive element. This is very non-polynomial. Okay. And the other way around, if you want to now go from s into x, then you have to write x as some infinite sum of some polynomials in s. But it's an infinite convergent sum. And basically, the way you do the calculation is that you do it on the Hilbert space. You realize that S can be represented as the unilateral shift on L to N. So if you want to have a faithful representation, you have L to N as a Hilbert space, and S of EI is equal to EI plus. That's it. And then the adjoint is S star of EI is EI minus. So you can see that S star S is equal to identity. Okay. And when you do Hilbert space representation for this relation, this is a weighted shift. So yes, this is so x acting on EI is EI plus 1, all right, but you have, I don't know, some square root of 1 minus q squared, whatever, maybe inverse, I don't remember. Okay. And when you sort of want to go from weighted to unweighted and back, you use these non-algebraic expressions and you are home and dry. So that's why q is irrelevant. Because you can always normalize it, and you can always normalize q away as long as q is not equal to 1.
Okay, so that's graph. What's the relations from this?
That's another story, which is yeah, but my time is running out. This is another story which is interesting. I mean, it's not obvious why the Teplitz algebra is the graph C-star algebra for this graph. But there is a certain procedure. If you would define graph C-star algebras without the second Kunz-Krieger relations, these would be so-called Teplitz algebras. Okay. So I just have only this SE star SF is equal to blah, 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 but I don't have a second Kunz-Krieger relation. Okay. But there is a beautiful theorem that tells you that every Teplitz algebra is a graph C-star algebra, but for a different graph. So given a graph and its Teplitz algebra, I can construct another graph so that this Teplitz C-star algebra will be isomorphic to the graph C-star algebra of a modified graph. So somehow I would have Teplitz algebra out of the simple graph. We just have one S and I have only isometry relation. Okay? If I don't have a second Kunz-Krieger, then Teplitz algebra for this graph is the Teplitz algebra. Okay, when's the name? because I don't have S star S equal to 1. I don't have a second constructive relation. But if I take the graph system algebra with the second constructive relation of this graph, is isomorphic. And if you want to prove the isomorphism, you just take this equal to S1, this equal to S2, and you'll have that S is mapped into S1 plus S2. And you can figure out everything. Yeah. The graph sister algebra of this graph is actually the sister algebra of Tetris, the quantum disk. Okay, in the remaining 2 minutes, since I have here 5 slides, I want to convince you that in fact you can do some amazing things with graphs, like in algebraic topology. So not only you can take the unions of graphs that will correspond to 2 surjective pullbacks of sister algebras, like you do with spaces. Okay, whenever I have a union of compact Hausdorff spaces, and I want to describe the union of a compact Hausdorff spaces, I describe it as the pullback sister algebra. Because what is the sister algebra of the union of spaces? This is a function on one space and a function on another space, and they must agree on the intersection of spaces. That's the pullback sister algebra. And the same holds for graphs. Okay, I can glue graphs together in order to have a glued graph, and then the sister algebra of this glued graph will be the pullback sister algebra of graph sister algebras of simpler graphs. Okay, so that works. But I can do even more, which is far more exciting. So you see, the way this Podlesh sphere is obtained is that you take the quantum disk and you shrink the classical circle boundary of a quantum disk to a point. That's how you get the Podlesh quantum sphere. And that's exactly on the picture. This is my quantum disk. This is its boundary circle. I shrink the boundary circle to the point and I get quantum sphere. And this is amazing that you can do this magic on graphs in non-commutative topology, things that are completely quantum. You can go further. Again, if you imagine a real projective space, a real projective space you can think of as the disk with the boundary points identified by antipodal map. So RP2 is a disk, but with the boundary circle identified by the antipodal action. Okay, so now you can do the same in the quantum world. You can do the sister algebra of quantum RP2. You can shrink that circle to a point and you get again the sphere. I mean, shrinking this circle in this disk in RP2 will also give you a sphere. The same is true in the quantum world. But you also have a quantum bonus. I mean, this is the Kunz algebra. This is completely non-commutative sister algebra. No ideals, 0. This is totally something quantum. I have a 1-point extension of one single extension of the sister algebra. This is some crazy non-commutative sister algebra. I shrink the Kunz algebra to a point. So I do the surgery on quantum spaces. I shrink completely, totally quantum space to a point, and what do I get? I get a sphere again. That's a quantum bonus because you cannot do it in the classical setting. But you don't think that all I get are spheres. Well, these are weighted projective spaces. Okay, so if you want, these are 2 kissing spheres. I have 2 spheres that kiss each other at the poles. Okay, and then what I do? This is the equatorial Polish quantum sphere. So this is the quantum sphere that you obtain by you have 2 disks, 2 quantum disks, and you glue them over the boundary circle, and then you get this graph. This is another quantum sphere, but now with a classical equator. But now if I shrink the classical equator to a point, I have 2 kissing spheres, and lo and behold, it all works. And I think this is the final slide. Yes, it's number 34. You have a CW complex structure for arbitrary Waxman-Soberman quantum complex projective spaces. So you can think about these projective spaces in the following way. I take a sphere which defines my projective space, and then I attach a higher dimensional cell, which is the ball bounded by the sphere, and this attachment gives me a higher dimensional projective space. This is exactly CW complex structure of complex projective spaces, as you know from school, and we, using graphs, can reproduce it for quantum complex projective spaces. So this was not done before viewing Waxman-Soberman projective quantum complex projective spaces as graphs. Okay, and I think this is the time to adjourn. Thank you very much for spending a month with me, and I hope to see you in Bendlevo in 3 Agosto next year. Thank you. I stop recording.